This week we're going to describe the mathematical equations that can be used to describe chemical reactions. Now I need to admit that I haven't taken a chemistry class for a long time, and being that most of you are biochemistry majors, you are much more adept at these ideas than I am, so excuse me if I say anything wrong. Point out next time I meet in class, but I'll try to do my best to keep the jargon correct. So our goal this week is to try to describe how concentrations of molecules get used up in a chemical reaction. And specifically, we're going to look at how this works for an enzymatic or enzyme catalyzed reaction. We're going to set up some equations, and then we're going to try to talk about what the solutions look like numerically, so we're using a computer to graph it, and then how to use some assumptions to reduce the equations down to something that we can actually solve ourselves. So let's start. Let's look at a simple chemical reaction where molecules of A combine with molecules of B to form this product we call molecules of C. So in terms of notation, A and B are the reactants of the chemical reaction, and we call C the product. And so some of the natural questions that come up is we know that concentration of mass requires that the amount of product equals the mass of the reactants, but how quickly do these reactions get used up? So how fast does the reactants get used during the reaction? What is the concentration? So how does the concentration affect the rate at which the reaction occurs? And maybe an interesting question, what will the concentrations be at equilibrium, so when the rates are balanced? So let's talk about this. So equilibrium, in this case, for example, doesn't make any sense because there's no backwards reaction, but in a moment we'll talk about what happens when we have a backwards reaction. So let's first translate our chemical reaction above. One thing to observe is that the concentration of A decreases at the same rate the concentration B decreases, and at the same rate concentration C increases. And since from calculus the rate of change is the derivative, this gives us information about the derivative of the concentration of A, B, and C. So when we say concentration, we're going to use these square brackets around our variables A, B, and C. So this is saying the concentration of A. Now we're going to say decreases, so we're going to put a negative sign to indicate that this value is going down. And that happens at the same rate which B decreases. And that happens at the same rate as C increases. So as we use up A and B, we produce this product in an equal rate. So negative signs for going down, positive signs mean going up. Alright, so now let's go up and let's talk about how to describe this rate in general. So we call the rate of reaction, or the velocity, V sub t. That's what this common derivative is going to be called, V sub t. It will have units of molarity over time. So molarity is 1 mole of solution per 1 liter of solution, and that's what A, B, and C are written in. Those are the concentrations of A, B, and C, the units of the concentrations. And so the V of t will be time dependent. So if the reaction is slow, like reactive decay, this might be a very small velocity, and time may be measured in years. If the reaction is fast, the time may be measured in milliseconds, and so the units of V will reflect those types of situations. The general rate law of chemistry says that during this reaction, the speed of the reaction is proportional to, so K here is the proportionality constant, or the rate constant. It's proportional to some powers of the amount of concentrations of A and B present. So A, alpha, and beta are the order of the reaction. And these constants, K, alpha, and beta, are typically only determined by actual chemical experiments. The units of K will depend on what alpha and beta are, because you can see on the left side we said that this rate of reaction is molarity over time. The units of K will then have to be multiplied by the concentrations of A, molarity to the alpha power, molarity to the beta power, and so we have, solving for units of K, the units of this constant rate reaction to be dependent on what alpha and beta are. Now, one of the limiting simplifying assumptions we can make is we can use the law of mass action. That's the idea we've been talking about with population interaction. That says, let's assume alpha and beta are 1. So that V sub t is just some constant, or is proportional to the amount of A we have and the amount of B we have. So only single powers, 1 and 1. So for example, with this velocity, we can now set up some differential equations for the amount of chemicals that are the concentrations of the chemicals during a chemical reaction. So let's do that in this case. So let's set up a differential equation for dA dt, dB dt, and dC dt. The first thing to notice is from our observation earlier that A is going down at the same rate that B is going down, and that C is going up. And now what we're assuming is that this rate, this B, is proportional to the concentrations of A and B, where we're going to assume this proportionality constant is given by 0.002. Sorry, 0.02. So we can then split this up into 3 equations. One for dA dt. So we multiply the negative to the other side, we get negative K1 concentration of A times concentration of B, dB dt. Also multiplying the negative both sides of those two sides of the equation, we get negative K1 concentration of A times concentration of B. And then our third equation is the right hand side of this part here. So dC dt equals K1 A times concentration of B. So you kind of see it as the rate at which A is used up is proportional to how much A there is, how much B there is. Same goes with B, and the rate at which C goes up is proportional to A and B. So that'd be a system of differential equations, all 3 of those equations, that describe the rate at which A, B, and C are changing in this chemical reaction. Now let's consider what happens if we have some back reaction. That is, some of the product can dissolve back into A and B. And we're assuming that happens with rate K sub minus 1. Then the equations become the following. We have the same equation for A as before with one modification. So we're losing A at a rate proportional to how much A there is and how much B there is. And then we gain some A by C dissolving back into that group. So we gain at a rate of K minus 1 of how much C there is. Same goes with B. Negative K1 A B K minus 1 of C. And then for C, its rate of change is 2 things are happening. It's gaining by A and B reacting with each other, and losing at some rate from what is currently there. Now if we take one of these equations, look at what happens when it's 0. So this would say it would be at equilibrium when the concentrations don't change. So if the concentrations don't change, and for example we take this equation and set the left hand side equal to 0, we can come up with a relationship between our rates. So let me write out this, and then we'll say these are at equilibrium. So these are the concentrations at equilibrium. If we add over the K1 A B at equilibrium equals K sub minus 1 C at equilibrium. And let's solve and compare Kn, so going to the left versus K out. So that's going to come from dividing this over to the other side and then bringing the C over to this side. That's a combination of A at equilibrium, B at equilibrium, over C at equilibrium. And that's usually what we'll call capital K at equilibrium. So what can we say when this value is bigger than 1? If capital K at equilibrium is bigger than 1, say a lot bigger than 1, maybe 10 to the third or something of that sort, then the concentration of A at equilibrium times the concentration of B at equilibrium over C at equilibrium is much bigger than 1, which means that A at equilibrium, B at equilibrium is bigger than C at equilibrium. So that would say that there's more reactants than product at equilibrium. If that value is roughly 1, then we could say that the amount of product is roughly equal to the amount of reactants at equilibrium. So product is roughly reactants, number of reactants.